All right, so this is lecture, I think, 22, I believe. So we're going to try to cover the whole topic of linear transformations. I actually doubted that we will be successful to do it today, but we will try to do that. So obviously, we will see today that matrices can be used to define what we call a linear transformation. But the message that is going to come from the lecture today, that linear transformations are way more general than matrices. Matrices is a way to do calculations with linear transformations, okay? There is no matrices in linear transformations. It's only a representation. The effect of a linear transformation can be represented with a matrix, so they are way much more powerful than matrices, okay? So we will see how matrices and linear transformations come together. Now, for those who really want to learn things, if you take other courses in the math department on linear operators, for example, or in functional analysis, you will learn much more than that. But also, some of you who will take courses in mechanics, the idea of, for example, of a tensor, it is much more general than a matrix, okay? But at the end of the day, when you try to implement things, you need linear algebra. Today we will see how all of these things can be generalized. Okay, so I'm gonna be doing a lot of jumping. So we define first a linear transformation. Okay, so we assume that we have some vectors v from some space, and you will see a formal definition shortly. And somehow we have a transformation t of v. T does something to v and gives me another vector in principle, okay? We have to put some rules on what exactly it means to be, for this transformation to be linear. And as you anticipate, the definition basically in general is the effect of this transformation on a linear combination of the vectors v and w should be c times t of v plus d times t of w. Okay? That's the linear combination that we have seen before, and that's what linearity for a transformation implies. Okay? And obviously, if you take here w equal to 0, you can write a specific case of this, that t of c times v is c times t of v. Okay? And here's one example. So this is a summary slide, but because sometimes the only thing we have left time-wise is to cover the summary, this transformation that you see here is not linear. Can somebody tell me why? So t of v, what it does is it takes every vector of v and it adds some constant vector u0. So it basically, it translates every vector by this constant vector u0. So why is this not a linear? It looks linear to me. So why it's not linear? Give me an example. Make it, you know, it's coming in some slide later on, but because we will not have the time most probably to reach that point, tell me now, why is this not linear? Give me one example. So if I take the vectors v plus w, all right? According to this transformation, t of v plus w will be v plus w plus u0, correct? Yes? That's the definition of the transformation. T of v plus w will be v plus w plus u0. But according to this, t of v plus w is t of v plus t of w, which means it's v plus w plus u0 plus u0. Yes? Who said yes? All right, I owe you $1. So t of v plus w is t of v plus t of w, which is v plus u0 plus w plus u0, so the two things are not the same. So something that looks linear, it may not be linear. So this transformation, by the way, is extremely important in applications. This is what we call an affine transformation, right? Just moving everything with some constant vector. So an extremely popular transformation. but it's not a linear transformation. All right, it's not a linear transformation. So something that looks linear may not be linear. All right? So the nice things with these transformations, right? So when I say you take a vector, this vector can be anything, actually. It can be a vector in Rn, can be a function, can be a matrix, can be anything, okay? So we will, if we have time, I'll show you examples where we actually are going to play with functions, okay, rather than vectors and matrices the way we have seen before. Okay, so the most trivial example, obviously, of a linear transformation is T of x equal A times x, all right, where A is some matrix, let's say m by n, okay? So you can actually verify immediately that this satisfies all the properties for linear transformations. So effectively here what we do is we take a vector x in Rn, and it returns a vector in Rm. So A, in general, is not a square matrix, okay? But obviously, there is not much to learn from a transformation T of x that is A times x, because in principle, we already have done those things with matrices. So we need something more general, but I want you to keep in mind that at the end of the day, there will be some matrix A that represents this transformation T of V, okay? So at the end of the day, to be able to do calculations, there will be some matrix representation, so we will see how that matrix representation comes about. So some examples from things that they don't look like vectors. So if this V that you have there is a function of x, right? You can define a linear transformation that is the derivative of f with respect to x. You can actually show all the properties for linear transformations are satisfied by the derivative. Okay? Actually, you can even go further and define a linear transformation on a function that is the integral of the function. All right? And you can show that this linear transformation is what we call the pseudo-inverse of this linear transformation, of the derivative linear transformation. And here, you know, we have not, I was planning to actually give you a lecture on pseudo-inverses, so maybe I will post something on the web if I find time. But obviously, you can appreciate that the integral cannot be the inverse of the derivative, because if you take the derivative of 1, what do you get? 0. Can you go from 0 to something? I mean, how can you go back from 0 to 1, right? It doesn't make sense. So this is what we call a pseudo-inverse, okay? So let's leave it there for now. And obviously, we will see also in examples this product of linear transformation. So when you see a product of linear transformations S and T applying to V, you basically have to apply this sequentially. So you first apply T on V, and then on the result, you apply S, okay? And actually, the powerful thing here is, because there are no matrices involved, right? This is an equation between operators, between linear transformations, okay? So we don't have to worry about, at this point, about matching dimensions and the like. Okay, so this is slide 4. So I can go to slide 5 now. And so people could discuss about linear transformations and operator theory. They are not linear algebra people, right? So they have their own terminology, even though they can use the same terminology we have used in linear algebra. So let's see what we have here. We have, so the linear transformation takes vectors from a space V and maps them to some space W. So these are the vector spaces we have defined in earlier lectures. This space V, all right, is called the domain of the transformation. Okay, that's the domain of the transformation. And W is called the codomain. And I see there immediately a picture that says the range. Can you tell me what you think most probably the next slide will say? What's the range of this transformation? How should we define it? Why there is, the transformation is from V to W, and I see now inside W, there is a little domain right, that we call the range. What is that, do you think? For example, do you think, in general, you can actually reach any point in the codomain by taking a point V in the domain and just mapping it? You think, in general, that would be the case? So what is the definition of the range of the transformation? Is all the vectors little w such that there is a vector V that is transformed to little w through the transformation T? Okay? And we call that the range of the transformation. All right. So we already said this, so we don't need anything. And so in this particular case, right, this little w is reached by this point V, and this is called the pre-image of w. This is actually an extremely important concept to know, okay? And generally, I am not saying that there is a single V that takes me to W. So there may be multiple V's that lead to the same little W. Okay? So the pre-image is basically what points in the domain lead to this little W in the range or the codomain of, of the transformation. Okay. So now I'm really going to do a jump in between. There are only examples that you will read. I will force you to read them through the homeworks. So I'm going to slide 17. And let me just put everything up. Okay? So there is nothing new here. Basically, that's the definition of a linear transformation. I split it, the linear combination, on two statements. All right, so this is for any, let's say, real C, positive or negative, T of CV should be C times T of V, okay? And T of V plus W is T of V plus T of W. Okay, so let me look at this. So we already discussed, actually, that the affine transformation, all right, so if you take this transformation, this is not linear, okay? We already discussed this. Now, I am going to immediately I'm going to say that if that T of 0 is equal to 0, can you tell me why is that the case? So if I take the 0 vector, and this is a linear transformation, then T of 0 has to be 0. Give me a proof of that. Otherwise, we're in trouble. So if I take the 0 vector, all right, plug it in there, T of 0 has to be the 0 vector. And just to motivate you in the proof, you can look at this equation there. So I said T of 0 has to be equal to 0. Look at this equation and convince me that T of 0 is equal to 0. So if we plug in V equal to 0, right, we're going to have T of C times 0 equals C times T of 0. So if T of 0 is not 0, all right, I can select the constant C to be what? 0. So the right-hand side then is going to be 0, but on the left-hand side, I'm going to have T of 0 times V, all right? So I'm going to have T of 0 equal to 0. Can you see this? If you take T of 0 not to be 0, okay, look at this equation and see what the left-hand side then comes to be equal to when C is equal to 0. It comes to T of 0 being equal to 0, which is a contradiction. So linear transformation needs to satisfy T of 0 equal to 0. Okay, if it doesn't, it's not a linear transformation. Okay. So here is another trivial example of a linear transformation. Suppose you have a fixed vector A, okay? And in this case is the vector 1, 3, 4. And you define the linear transformation as mapping these vectors in R cubed to scalars and it's defined through the inner product of A with V. So A, again, is a fixed vector. So this is the definition of the linear transformation, okay? And actually, you can immediately see, you can write this linear transformation as a product between a matrix and a vector. You can write this in the form AV, where A is 1, 3, 4, and V are the Cartesian components of the vector V. Right? It's the same thing. I'm making now a connection suddenly of a linear transformation with a matrix, okay? But generally, we will have to do much harder work to actually figure out what's the matrix representation of this transformation. But in this particular case, the inner product is nothing else but, the inner product of 1, 3, 4 with V. So if you take a vector A to be this row vector, right? So A times V is the inner product. Okay. Convince me, okay? I mean, I should not have shown all the results there, so don't read them. Can you actually, looking only in the first line, convince yourselves that if you take a linear transformation operating on V to give you the magnitude of V, that this is not linear? I mean, I'm going to take only one of the results, right? So let me take something different before we use the multiplication with a scalar. So according to this, right, this is my linear transformation. If it is a linear transformation, is if I operate on V plus W, according to the linearity, this should be equal the magnitude of V and the magnitude of W. But is this equation correct for vectors? What's the correct equation? Who defines the correct equation there? That the magnitude of V plus W is what? What my friend Pythagoras said. Less or equal to V to the magnitude of V plus the magnitude of W. They're not equal. Okay? And similarly, you can show that this other equation is not actually true, all right? So linearity will imply this, but if you take C to be negative, all right? I mean, if I put T times minus V, the magnitude of V and minus V will be the same. I am not going to get minus the magnitude of V. So this fades again. Okay, so this is not a linear transformation. Supposed to go to, okay, I missed this. Now, why we jumped to 22? Okay. Don't let him sign that piece of paper. That's your task for today. Okay. Let me keep moving. So let me go to slide 25 to see geometrically what it means. Oh, no, 25. What it means to be a linear transformation. All right. So just to get a geometric interpretation of things. So consider that you have defined two vectors, and I'm looking on the plane now, the vector V and W, and I move V to T of V and W to T of W. The idea geometrically of a linear transformation means that if, in principle, you take any point in the line connecting V and W, the image actually of all of these points, so if you take any U, T of U is going to be on the line connecting T of V and T of W. That's what a linear transformation means. All right? So in this particular case, I take V, the transformation moves V by, let's say, horizontally. W moves it horizontally to T of W. So if you take, let's say, the point U in the middle of V and W, then T of U will be 1/2 of T of V plus 1/2 of T of W. Okay? And you can see this actually with three vectors. So if you take these vectors V1, V2, V3 that are mapped to this new triangular TV1, TV2, TV3, you can actually, if you take the center, let's say, of this triangular, is going to be mapped to the center of the triangular with edges T of V1, T of V2, T of V3. So that's sort of the geometric interpretation of linear transformations. Let me see, go to slide 27. All right. So what good are linear transformations, right? And how are we going to use them to do any algebra? So let's do the following thing. We have shown, right, from linearity, that if we take, let's say, the vectors v1 to vn, and we form this linear combination c1 of v1 and cn of v1, then t of u is equal to this. Everybody agrees? Right? This is the result of linearity. If you take as an input vector a combination of v1 to vn, then t of u is a linear combination of t of v1 and t of vn. Can you tell me now why this equation may be useful? It says something that if you want to find the effect of the transformation on a vector, the only information that you need to have at hand is what? So if I give you an arbitrary vector u, let's say, the only thing that you need to compute t of u is what? According to this equation, you have to extrapolate a little bit. You have to make these vectors v1 to vn special vectors. I mean, if any vector u can be written as a linear combination of v1 to vn, what are v1 and vn? And they're independent. They're the basis, let's say, of the input space, of the domain of the transformation. So according to this equation, if you know the effect of the transformation on the basis vectors, you're done. You can compute the effect of the transformation on any vector. That's a major thing, all right? So effectively, the only information that we need to collect to be able to use this transformation is to figure out what is the effect of the transformation on each basis vector v1 to vn. As a matter of fact, I'm going to throw at you now, early on, even though it may be coming 20 slides down the road, that if somehow you compute t of v1 and t of v2 and t of vn, and you put each of these vectors as a column of a matrix, that matrix defines the transformation for that particular basis. Because effectively, the effect of the transformation on u will be the product of that matrix times the coefficient c1 to cn. You see that? So again, let me just say, if you compute t of v1, t of vn, and you make this the first column of a matrix A, and this the nth column of a matrix A, effectively to find t of u, you have to multiply that matrix A with the coefficient c1 to cn, right? That define basically the vector u in the basis v1 to vn. Okay? All right. So I'm not going to do these examples. So let me go to slide 29. Actually, I already told you there's nothing on slide 29, okay? It's basically what I discussed, okay? So we're done. So let me do one example. And actually, this will be an adventurous example, okay? So, come on. Actually, if this has, okay. Maybe I should go back. So let me discuss the example of the linear transformation that takes derivatives of functions, okay? Because obviously everything is not just about matrices. So we have a function u, and we define a linear transformation that is du over dx. So let's say that the input, the domain of this linear transformation involves constant values, linear and quadratic. So this is a typical u, all right? So you start basically, what is the basis? If u is written like that, can you tell me what is the basis in that function space? Before we had vector v1, v2, vn. So what's the basis here for if the input contains linear terms, constant terms, and quadratic? What's the basis for that space? What's the basis in that space? 1x and x cubed and x squared, right? So the basis is 1, x and x squared. And what is the basis actually for du over dx? So after you differentiate, if the input contains constants, linear and quadratic terms, what's the basis actually for du over dx itself? What functions you will contain? If you differentiate quadratic terms, what do you get? What do you get? You get linear terms, right? And you get constants. All right. So let's say that you want to compute the derivative of u equals 6 minus 4x plus 3x squared. You know, actually what you do when you learn calculus is you take 6 times the derivative of 1 minus 4 the derivative of x plus 3 times the derivative of x squared. And that is what? What I just said before, right, with the basis vectors, isn't it? So actually, the whole of calculus will be out of the window if this concept of linearity is not applied. Literally, calculus is directly connected with linear algebra. One will not make sense without the other. Okay? So, and actually, the only thing that somehow linear algebra is not going to help you is the chain rule. So if you try to take derivatives of f of g of x, okay, that requires a little bit more calculus thinking. Okay. All right, so I'm not going to discuss that slide, so we can move on. So there is, I kept notes of the slides, so let me see what slide it's supposed to be. Slide 40. All right, so we're jumping to slide 40 to do the matrix representation of this derivative operator. So what's the matrix for du over dx? So again, I explained, right? If you have a basis for the input space, you can find the effect of the transformation on each basis vector, and you can define basically a matrix that contains T of V1 as its first column, T of V2 its second column. So that matrix A times the coefficient C1, C2, Cn, it tells you what the operator does on any vector that's a combination C1 of V1 and C2 of V2, etc. So let's see this for derivatives so you can get your imagination running a little bit wild. So we need to find the derivative of d over dx. And I am going to take my basis vector, since you told me so, to be 1x and x squared. Right? That's my basis. You can repeat this example with sines and cosines and everything. So we're going to use 1x and x squared. So obviously, the effect of the linear operator, the derivative on V1 is 0, on V2 is 1, and on V3 is 2 times x, which is 2 times V2. Can you tell me, assuming now that I am guessing there must be a matrix somewhere, how does that matrix will look like? Convince yourselves that that matrix looks like this. Now, first, why this matrix is 2 by 3? The 3 comes from where? I told you, take T of V1, make it one column, T of V2 another column. So the 3 comes from what number? Why do I have this matrix to be 2 by 3? The 3 comes from where? Say it again. How many basis vectors I have, right? I have 3. So I have T of V1, T of V2, T of V3. And why I have only 2 rows? Because I take each of this T of V1, T of V2, and I represent it in the basis of the derivative space. And in the derivative space, if my input contains 1x and x squared, what type of vectors do I have in the output? So if you take something that is quadratic and you differentiate, what do you get from it? You will get a constant end and a linear term, right? An x. That's the constant, the first term, and that's the linear. So can you tell me now where the 0, 0 comes? What is the 0, 0? So the first column should correspond to what? The derivative of which vector? 1. And how much is the derivative of 1? And what are the components of 0 in the basis of the output, which is, you told me it's constant 1 and x? 0 and 0. Nice. How about the derivative of x now? What's the derivative of x? I see 1 there and 0. And what's the derivative of x squared? 2. Right? It's 2x. Done. That's the matrix that represents this derivative operator, linear operator, right? For this particular case of my basis vectors being 1x squared for the input, and then recognizing the output would have only constant and linear terms. OK. So for example, if you want to find the derivative of a function that is now u equal a plus bx plus cx squared, this is my coefficients that I had before, C1, C2, C3, right? So what you need to do is take that matrix A and operate it on ABC. And what is ABC? Are the linear combinations of the basis input vectors that I had. So suddenly we transform the whole problem of computing derivatives to a linear algebra problem by recognizing what this matrix A is that defines this linear operator. Can you see that? This is for my audience. You know, this is the most silent class I experienced this Wednesday. OK? And I noticed you keep going backwards and backwards, and you make me walk and lose some weight. All right. Clear? Yes? All right. So let's see, we're slide 41. Can I do the same thing? I am not going to repeat this, right? But can you imagine if you can do this for integrals? Can you do this for integrals? Why not? I mean, if, for example, if you take, I don't want to repeat it, right? If you take a function that has constant and linear terms, when you integrate, you will get a linear term, and you will get a quadratic term. So the input now contains 1 and x, and the output contains what? X and x squared. So if you actually, and actually the output here, I have to include also the constant term, right? So the output contains 1x and x squared. If I don't do this, the integral is not going to be looking like the pseudo-inverse of the derivative. So I'm just going to give you the result. There it is. This pseudo-inverse, and I put a plus because we haven't really formally defined the pseudo-inverses, but it's basically this matrix that takes these combinations of 1 and x, my input basis functions, and tells me what the integral is. Nice. We learned how to calculate integrals. You forgot, right? OK. You know, the thing is, the nice thing about mathematics, right, is that they're clean. You cannot lie. You cannot lie. It's not like, oh, I think this times that, you know, it looks good, and, you know, you can go to the moon. No, you cannot. Mathematics don't lie. You have, you know, if you do it properly, everything is nice. And if you don't really care about mathematics, you should care about the way mathematics think. Because if you learn that way to do all of your engineering work, you will do very well. But if your thinking is disorganized, like not saying this leads to this, to that, because of this and this, you know, I get that. If you jump from here to there in an arbitrary way, you will come up that the integral is actually the inverse of, I don't know of what, but not of the derivative, OK? You will come up with something else. OK. So let me go to slide 53. I don't know if we're going to manage to finish what I wanted today, but let's do slide 53. If I take a projection, of a vector in R cubed, all right, so here is my vector x, y, z, and I project it to the plane defined by z equal to 1. Is this a linear operator? Is that a linear transformation? Give me one reason why is this not a linear operator. T of 0 has to be equal to 0, and obviously this is not going to be ever equal to 0 because of that 1 there. So these projections, you have to be very careful. They are not linear operators. All right? I don't need anything about the inverse. You can imagine what an inverse operator does, right? So let me go to 55. There's nothing new there. So the only thing I'm going to mention, because I just see it there, and you can extrapolate this from the derivative example, right? We have a basis to describe input vectors, all right? And then we have another basis to describe the output of the transformation, all right? So there is an input basis, all right? And there is an output basis, and generally speaking, they're not the same. Okay, if it happens that they are the same, all right, algebra looks very simple, but generally the input basis is not the same as the output space. So, for example, we use for the derivatives, we use 1x and x squared for the input. The output was 1 and x, okay? So the input basis and the output basis is not the same. All right, so let me put all of this thing up and discuss a little bit about the change of basis. And I think we actually have maybe enough time to actually complete this in some superficial manner, okay? So, as a reminder, we have a basis V1 to Vn in the input space. We compute the effect of the transformation, TV1 to TVn, and then we take each of these vectors. In principle, we represent it in the output basis vectors, and we form this matrix A, okay? So, you know, for example, here, if you take the vector Vj, you expand it on the output vectors W1 to Wm, and these coefficients go to the jth column of the matrix A. The key thing here is two things, right? You take the effect of the transformation on the input basis vector j, and you write it as a linear combination of the output basis vectors. All right? So for example, maybe the input vectors are in Rn, the output vectors are in Rm. You're not going to use the same basis. And these coefficients go to this matrix A, and the transformation actually will look like A times x, where what is going to be x? For every vector v, x is going to be the coefficients that define that vector v as a linear combination of v1 to vn. And what will be the output? There will be the coefficients that define the vector t, let's say, of a general vector v in terms of the basis functions w1 to wn. Okay? All right. So it says there, and you're going to have to explain to me what it means because my brain's frozen. It says the matrix for t of x equal to ax is A if the input and output bases are the columns of the identity matrix n by n and the identity matrix m by m. So let's say if my input is Rn and my output is Rm, it says if you're going to write t of x is equal to A times x, all right, this is only if the input and output bases are the columns of the identity matrices. What is the implication here? You remember, you know, if you have, you know, what is the standard basis in Rn? Give me the basis vectors in R cubed, for example. What are the standard vectors? What is the standard basis vectors in R cubed? 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay? And similarly in Rm, so if you take the input to have that basis, all right, defined by the columns of this, and the output to be defined like that, then t of x becomes A times x, okay? Where x basically are your coordinates, all right, the coordinates of that vector in the standard basis 1, 0, 0, 0, 1, 0, 0, 0, 1, okay? Here is the tricky part. if you choose arbitrary basis for the input vectors v and the w's, defined by these matrices v and w. So v and w are the matrices that have in their columns the basis vectors v's and the basing vector w's. Then the matrix A changes to w inverse times A times v. This is not trivial. So if you change your input basis, right, to contain the vectors v1 on the first column, v2 in the second column, and form this matrix V, and you change the output vectors to represent the output in the vectors w1, w2, wn, then the representation, the matrix representation of this linear operator is w inverse A times V, where A is the matrix that you get when you use the standard input that you described to me, 1, 0, 0, 0, 1, 0, etc. So I want you to, before we do any calculation, somebody to actually help me with this. Can anybody actually foresee why, by changing the basis, somehow the linear matrix representation of the matrix changes? I mean, we don't care about the result, but can you tell me, if I have an operator, right, and I represent my input in the standard basis or in the basis of these vectors v1 to vn, do you agree with me that matrix should look different? Right, because the input vector is different. Can you see that? I mean, if I describe a vector and its components in the space 1, 0, 0, 0, 1, 0, 0 in that basis versus some other vectors v1 to vn, don't expect the matrix to be the same, right? So can you see where that, what that v does? That v transforms from the coordinates of any vector from what basis to what basis? If you help me on that, I'll be happy. It transforms from the coordinates in the v system to which basis? Remember, this matrix A, the way I define it, is defined for the standard basis. So if I want to calculate what this operator does to a vector represented in the v basis, what do I have first to do to this representation of the vector before I operate with A? I have to transform it from a representation in the v coordinates to what coordinates? Unit coordinates or the standard basis. And what is the matrix that does that? Is the matrix V. So this matrix V, what it does is it takes a representation of a vector in the v1, v2, vn coordinates, and it transforms it to what representation? To the standard basis 1, 0, 0, 0, 1, 0, etc. Then I operate on the new coordinates in the standard basis with A, because that's what A is defined. And what do you think W inverse does? The result of A times V times a vector written in the V coordinates, right? It's a vector now in the standard basis, 1, 0, 0, 0, 1, 0, 0. But I want my output to be on what basis? I want my output to be on the basis W1, W2, Wn. I want to go back now. And how do you go back? With W inverse. Again, let me describe with words this, right? Algebra is not important. A is a matrix that takes, we define A as a matrix that takes the coordinates in the standard basis, 1, 0, 0, etc., and it gives him the output in the standard basis. We call that A. If we want to find the matrix that represents this operator in a way that it takes vectors represented in the V coordinate system and gives me the output in the W coordinate system, what I need to do is to use this A. I have first to transform a vector from the V coordinates to the standard coordinates, and I do this with a matrix V that has in its columns the V vectors. Operate on A. The result will be now in the standard basis, and I have to operate with W inverse to go back to what basis? The little w basis. So basically, a vector So this representation that you see here is the representation of the linear operator, where you operate, if you use this expression, you operate on a vector in the v coordinates, and the answer is a vector representing what coordinates? What coordinates? In the w coordinates. All right, where v and w can be any basis for the input and the output spaces. Okay? So let me, I am going to give you an example, if I can find it. Let me go to slide 70. Actually, not even slide 70. Let me go, because I don't have time, slide 72. 72, let me see. 74. Okay. Let me do this. Let's assume that the linear transformation is the identity transformation. Can you tell me what is the identity transformation should do to a vector v? T of v should be equal to what? For an identity v. All right? Now, somebody will say, what is the matrix corresponding to the identity linear operator? What will you tell me? In particularly, what does that metric say if I use the standard basis for the input and the output for the identity operator? The identity matrix. So A, remember, is the identity matrix. Now, I am telling you, I don't want my input to be on the standard basis. I want it to be on the V basis, and I want the output to be on the W basis. So according to that formula that I had before, if it is correct formula, what the answer will be for the matrix representation of the identity operator? Will be W inverse times the identity times V. So let me prove it to you for the identity operator, and then you can start extrapolating. Take an arbitrary vector u, right? You agree with me that the linear operator will not change u. Because when I say vector, I don't mean with any representation. A vector is a vector. It's invariant. The transformation doesn't change u. Okay? So what have I done on the left-hand side, and what have I done on the right-hand side? Look at it and tell me. What is C1 to Cn? What is C1 to Cn? Look at that equation there. All right? So what is C1 to Cn? Is the representation of u on what basis? Say it. C1 to Cn is the coefficients representing u on what basis? V. And what is D? Is the representation of the same vector u on what basis? W. So will you agree with me that in a matrix form I can write this V matrix, so every vector V is the column, times the C vector, equal to W times the D. And what do we want? We want to have the input vector in what space, in what basis? We want to have the input vector in the V basis, and we want to be the output on what basis? The W. So what do we want to be our input, and what we want to be our output in terms of this coefficient C and D? Remember, this is the identity operator, right? So U doesn't change, but the representation is going to change because we start with a representation with these V vectors and go with a representation with the W vectors. So what do we really want to do? We want to compute these coefficients D1 to Dn. And what are these coefficients D1 to Dn? Is the inverse of W times V, all right? And that's our matrix representation when the input is given in the V basis and the output is given in the W basis. Can you see that? I mean, this is the equation basically. The input C is the representation of the vector in the V coordinates, right, in the V basis. And the output is the representation of the vector in the W basis. So our new matrix becomes W minus 1 V. So something that looks like a nice identity, now from a nice identity, has been transformed to W minus 1V because I use bases that they're different from the input and different for the output. Let me just actually, since you are here, okay, and we have 2 seconds to go, or 2 minutes, if I can find this, actually, let me go to slide 104. All right, look at this equation that is given in here, okay? So I am just telling you I have some operator, it's not anymore the identity, and I define a matrix A where I use the standard input, right? I use the standard input for the input and the output, and that's my matrix A standard. Now I want to transform both the input and the output with the same basis, but it's different from the standard basis. Will you agree with me that if I define a matrix B now that contains the basis in that, let's say, in V1 to Vn that I had before, will you agree with me that the new matrix is going to be B inverse times the A standard times this matrix B? So this matrix B takes you from this new basis to the standard basis, and the inverse takes you from the standard basis to the new basis. Okay? So the transformation, basically, before we had it for the identity linear operator, now I have it for an arbitrary operator that leads in the standard basis to some matrix A standard. When you look at this equation, does it remind you anything? Like B inverse times A times B. Say it again. B inverse times AB. What does it remind you? B inverse AB. Diagonalization, the spectral theorem. You know what? You can actually use the singular value decomposition in selecting appropriate matrices B, all right? And in that case, you can take an operator that is, leads to a complete full matrix A in the standard coordinates, and then the new coordinates, when you use these matrices by using the SVT decomposition of this new matrix is going to become what type of a matrix? Before the light goes on, it will become a diagonal matrix. So the transformation has a special basis that leads to diagonal matrices, and don't sleep in my class. Not very good for you. Okay? You can break your neck. All right, so I'll see you on Friday.